Hey, welcome to our explainer. Today we're diving into two forces that are so powerful, so fundamental, they basically run the show, but we hardly ever think about them. We're talking about gravity and friction. These are the invisible rules of our universe, and we are about to pull back the curtain on how they really work.
So, let's kick things off with a little puzzle, something that seems to completely defy common sense. Imagine a special room where, if you drop an apple and a feather at the same time, they hit the floor at the exact same moment. How on earth is that possible? Stick with me, because by the end of this, you'll know exactly why.
To crack this puzzle, we have to start with the main force in the picture. It's the force that keeps you in your chair right now and keeps the entire Earth circling the sun. You guessed it, we're talking about gravity.
So what is gravity, really? Well, it's this fundamental force of attraction that exists between any two things that have mass. I mean, anything. You, your phone, the planet, a distant star, everything is constantly pulling on everything else. And it's a non-contact force, which just means stuff doesn't have to touch for it to work. And here's the key. It always pulls, it never ever pushes.
Now, this brings up something that trips a lot of people up. We tend to use the words mass and weight like they're the same thing, but in the world of physics, they are totally different. So let me ask you, is your mass really the same as your weight?
Okay, so here's the breakdown. Your mass is, simply put, the amount of stuff you're made of. It's measured in kilograms, and it never changes, whether you're on Earth or floating in space. Your weight, on the other hand, is the measurement of gravity's pull on all that stuff. We measure that in newtons, and it can absolutely change depending on where you are.
Let's make this super clear with this robot, for instance. On Earth, its mass is 50 kilograms. If we take it to the moon, guess what? Its mass is still 50 kilograms. It's made of the same parts, right? But look at the weight. It's 490 newtons here on Earth, but on the moon, it's just 81 newtons. Why? Because the moon has much weaker gravity, so it's pulling on the robot a lot less. See? Same stuff, different weight. The cool thing about gravity is that it's not some random, mysterious force. Its strength is actually predictable, and it all comes down to two simple factors. Once you get these two rules, you can figure out the gravitational pull between pretty much anything.
All right, rule number one is mass. It's super straightforward. The more mass something has, the stronger its gravitational pull. It's the reason you're being held down by the incredibly massive Earth, but you don't feel a pull toward the person sitting next to you. Their mass is just way too small to have any effect you'd notice.
And the second rule is distance. The farther away things get from each other, the weaker their gravitational pull becomes. This is exactly why rockets have to burn so much fuel to get far away from Earth. They're trying to escape that pull. The farther they go, the weaker it gets, until eventually the gravity of other planets or the sun starts to take over. Okay, so that's gravity. But it turns out gravity isn't acting alone, especially not here on Earth. There's another major force that's almost always part of the equation, a kind of resistance. Let's talk about friction.
And to really get a feel for friction, let's try another little puzzle. How is it possible that you can lift an entire flask of rice with nothing but a single chopstick? I mean, if you just place it in there gently, it'll slide right out. But if you pack the rice in tight and then stick it in, the whole thing lifts up. What is going on there?
The secret, of course, is friction. Friction is a contact force that always tries to stop motion between two surfaces. When that rice is packed in super tight, all those little grains are pressing against the chopstick, creating a massive amount of friction. That frictional force is actually stronger than the force of gravity pulling the flask down, which is why you can lift it all up. Pretty cool, right?
And the thing is, we're constantly trying to control friction in our everyday lives. Sometimes we want a ton of it. Think about the brake pads on your bike, or the grippy soles of climbing shoes. But other times we want as little friction as possible, like when we oil a bike chain or use ball bearings and wheels to make things move smoothly. It's this constant balancing act.
And that brings us to the last piece of our big puzzle, a very specific type of friction called air resistance. You see, as anything moves through the air, it's constantly bumping into tiny air molecules. All those little collisions add up to a force that pushes back against the object's motion. And this right here is the hidden clue that explains everything about our falling apple and feather.
All right, let's put it all together. We have our two main players, gravity, pulling everything down, and friction, in the form of air resistance, pushing everything up. With these two forces in mind, we can finally solve our mystery. So let's get back to it. Our brains tell us that an apple drops like a rock and the feather just kind of floats down. So why in the world would they ever fall at the same speed? Here's the solution, step by step. On Earth, you're right, gravity pulls them down. But air resistance pushes up. A feather has a huge surface area for its tiny weight, so it catches a ton of air, which slows it down a lot. But, and here's the trick, that special experiment takes place in a vacuum. And in a vacuum, there is no air, so there's no air resistance. The only force left is gravity, and it turns out, without air in the way, gravity pulls on everything at the exact same rate, no matter how heavy or light it is. And just like that, mystery solved.
But look, understanding all this isn't just for solving cool physics puzzles. It's absolutely essential for how we design, build, and interact with the world around us.
Take a parachute, for example. The entire point of a parachute is to fight gravity by creating as much air resistance as possible. By making it really wide, you increase its surface area. That huge surface area catches a massive amount of air, generating a powerful upward force that slows you down enough for a safe landing. It's all about managing friction.
And gravity's influence stretches way, way beyond just things falling to the ground. It's the force that literally holds the moon in its path around the Earth. It's what keeps all of our communication and GPS satellites up there in orbit. Without gravity's constant pull, they'd all just fly off in a straight line into the darkness of space.
You know, our whole idea of what gravity even is has changed over time. Back in 1687, Isaac Newton gave us the classic idea of it being a pull between two objects. But then, in 1915, a guy named Albert Einstein came along and completely revolutionized how we think about it.
Einstein's idea was mind-blowing. He said that gravity isn't really a force at all. Instead, he pictured space and time as being woven together into a single fabric. He called it space-time, and massive objects like a planet or a star actually cause this fabric to bend and curve. The classic analogy is putting a heavy bowling ball on a trampoline. It creates a big dent, and that dent is what we feel as gravity. Other smaller objects are just rolling along the curves created by the bigger ones.
So think about that. We started with a simple question about an apple and a feather, and we ended up with the idea that gravity literally bends the fabric of reality. The simple forces we see every single day are tied to the deepest, most profound mysteries of the cosmos. It really makes you wonder, if that's true, what other incredible secrets is the universe just waiting for us to figure out?